course CE07 Structural Dynamics, and I am your uh, teaching instructor Harshit Agrawal. So, in today's session, we will cover following things. First, what was taught in week 1, a brief overview just to brush up the content and get everyone on the same level. Additional point that I find everyone must know, which will help you for solving assignments of NEPTIL as well as in general understanding. Then there will be a series of 5 questions, each one different from the other, based on the content covered in the week 1 and assignment 1. I will first try to explain you the question, and then step by step we will solve the question. So make sure you all have a pen and a paper beside you so that you can solve along with me. Finally, we will look into how the theoretically the things we solved can be visualized through a MATLAB code. So I step by step will guide you how to code in MATLAB, and we will see the results. So if you have access to MATLAB, just keep it open in your laptop or PC. Else just write syntax along with me and try to replicate it later on. And if any doubts, can ask me in the next live session. So I hope everyone are clear with the instructions. If you have any doubt, can raise hands or write your query in the chat box. I'll respond as soon as I will see. So let's start. During the week 1 of structural dynamic course, we learned about undamped free vibration. What it is, these are the structures which vibrate under their natural initial vibration and no externally induced vibration. So what are vibrations? Vibrations are just simple oscillatory motions. And in the modules of week 1, they were distributed into following content. First, we learned about classification of types of analysis based on force, material, and deformation level. So according to force, analysis can be classified into two types. First is static analysis, that is the applied force is constant and deflection is directly proportional to force. And second is dynamic analysis, where applied force varies with time. Now, second classification is according to material behavior, in which there are two types: linear analysis, where load are well within the elastic deformation range, and Hooke's law and superposition principle are valid. And second is non-linear analysis, where loads are beyond the range of elastic deformation, and thus superposition principle are not applicable. And finally, based on deformation level, where we have two things: small deformation, where analysis is confined to only primary effects like material nonlinearity. And second is the large deformation, where we consider the secondary effects also, like buckling, P delta effects, and everything. Then we looked into degree of freedom and stiffness matrix, where we first saw the three equilibrium equation of static equilibrium. We read about static indeterminacy, kinematic indeterminacy, and then we saw the calculation of stiffness matrix when a unit rotation or unit displacement is given, and the far end is hinged or fixed. Then we saw vibrations in single degree of freedom system, where we wrote the dynamic equilibrium equation from Newton's second law, and we saw different vibrations of a system, different classification of vibration of system, which are broadly classified into two types: free vibration and forced vibration. And within these, we have two subcategories of undamped and damped vibration. After this, we saw the methods of solution of equilibrium equation, where we read about classical method, Duhamon's integral, and transform method. These three are used for linear system, and fourth one was numerical method, which is generally used for non-linear system. And finally, we saw about undamped free vibration, where we derived the equation of displacement versus time for undamped free vibration. Mr. Mayur, I have just started the content, and you can join me. So Till now, I've given the overview of what has been taught in week one, and now we will start with the content ahead. If you have any doubts in between, you can ask. Okay, so apart from whatever you have read in the week one additional point that I will like to cover is the equivalent spring constant. Now, some of you may know how to calculate this, but still I will repeat for those who are not aware of this. The figure in the left shows a frame resting on two columns and under an action of an external force. And figure in the right shows the equivalent spring block system for this frame. You have read about this during the NPTEL lectures of week one. Now, suppose these two columns have different material properties. Now, so it is not necessary, it sometimes it becomes necessary to determine equivalent spring constant where there are two or more springs arranged in parallel or series. And how it can happen? Suppose there are two columns which have different material properties or geometric properties, so they won't be able to offer the same stiffness, right? Thus, we need to know how to calculate equivalent stiffness, and such systems comes under case 1, springs in parallel. So, if the two columns have different properties, the spring block system for the frame system will appear like this. And in this case, for the two springs in parallel, the total force required to produce the relative displacement at their ends of one unit is equal to the sum of spring constant. So here the total equivalent spring constant becomes Ke is equal to K1 plus K2. Now suppose we have a multi-story building, multi-story frame. So we may have more than one column on either side of the frame. So in this case, this is case 2 where springs are in series. And in this case, the spring block system may appear to be like this. And thus, in this case, for the springs assembled in series, the force free produces a relative displacement, total relative displacement of delta U1 and delta U2. And in this case, the equivalent spring constant is given by 1 upon K is equal to 1 upon K1 plus 1 upon K2. So this was one additional point that I wanted to cover for week one. Now we will see questions based on the week one content. Anytime you have any doubt, you can raise your arm, you can raise your hand or write your message in the chat box, and as soon as I will be able to see the meet link, I will respond to your doubt. So, first question. The question is show that the same differential equation is obtained for a body vibrating along a horizontal axis or for the same sorry for the distance or for the same body moving vertically in an undamped free vibration. So during the course content we saw that a frame structure can be represented into a equivalent horizontal spring block system. Now for an undamped free vibration means that there is no external force. So Pt is equal to 0, and since it is undamped, so C is equal to 0. And the dynamic equilibrium equation for this is mu double dot plus Ku is equal to 0. Now, when will this equation hold true if my body is vibrating in vertical direction also? Here you can see the spring block system is representing a horizontal vibration of the frame. But will it hold true if the body is if the spring block system is vertical or not? That we will see. So when the body is in static equilibrium, there will be initially a little displacement in the spring, and that will be equal to the weight of the mass. So I can say Ku naught is equal to weight of the block. Now suppose I have given it some displacement U to the body. So I have, when the body is displaced by a distance U from its position of equilibrium. So what will happen? There will be one force. First, there will be a spring force which will be acting upward, and the value of it would be K times U naught, which is the initial displacement at equilibrium position, plus U, which is the displacement that we have provided to the system. And this force will be acting upward. Second will be the weight of the block, which will be acting downward. And third is the inertia force, mu double dot, which will be acting upward. Why inertia force is acting upward? It is due to the D'Alembert's principle that we have seen in the course content, that a moving mass always generates an inertia force opposite to the motion. So, using Newton's second law of motion, we can say k times u naught plus u plus mu double dot minus w is equal to 0. And from initial static equilibrium relation, we know ku naught is equal to w. So we can say, substituting ku naught is equal to w in the above equation, we will get mu double dot plus ku is equal to 0. So this proves that the same differential equation is obtained whether we are converting our frame structure into a horizontally vibrating system or a vertical vibrating system. This was just a proof question that I found is needed to be included in the content. And now next we will see all the numerical questions. I hope everything is clear till now. Okay, so let's proceed ahead. Thank you, Mayur. Let's proceed ahead. So, second question. In this question, it is given, determine the natural frequency of a beam spring system shown in the figure, consisting of a mass of 5 kg attached to a horizontal cantilever beam through the coil spring K2. The cantilever beam has a thickness h is equal to zero point 0.5 mm, a width b equal to 1 mm, and is made of concrete of grade M20 and length L equal to 12.5 mm. The coil spring has the stiffness of K2 is equal to 20 mm. So in the figure you can see we have a fixed support and a cantilever beam. The properties of cantilever beam is given in the question. The thickness 0.5 mm, width 1 mm, grade of concrete 20, which is used to make the cantilever beam, and the length of the beam is 12.5 mm, and there is a coil spring of stiffness coefficient 20 newton per meter millimeter square, and at the end of the coil spring there is a block mass block of 5 kg attached. So we need to determine the natural frequency of a spring of this spring block system. Okay, so natural frequency of a system is denoted by omega n, and it is equal to k equivalent upon mass, under root of k equivalent upon mass. Now we know mass is equal to 5 kg, but what is k equivalent? K equivalent is not just k2, it is the equivalent of both cantilever beam and the spring. So we need to calculate the k equivalent in this case. And the theory for this we covered just a while ago, where we talked about springs in series and springs in parallel. So step one is finding the K for the cantilever beam, because for the cantilever beam we have given the data of its dimension, its grade of concrete, and not the K and not the stiffness coefficient. So we will first find the stiffness coefficient for the cantilever beam. So for the cantilever beam acted upon by a static load at the end, the stiffness coefficient is given by 3 EI by L cube. That you know. Okay, now we know L, but we don't know what is E and what is I. So first we need to estimate E, that is the elastic coefficient, and I, that is the moment of inertia. So modulus of elasticity is when the grade of concrete of the cantilever beam is given according to IS 456. The modulus of elasticity of the beam is denoted by 5000 under root FCK. And FCK value we have been given as 20. So the modulus of elasticity will come out to be, after calculation, 22361 Newton per mm square. Okay, and second is the moment of inertia. So moment of inertia of beam is denoted by BD cube by 12, and we know the width of the beam is 1 mm and the depth is zero point 0.5 mm, that has been given to us in the question. So 1 into zero point 0.5 cube upon 12, that will come out to be 0.01042 millimeter to the power 4. So now we know the modulus of elasticity and the moment of inertia. So we can calculate K as 3 EI by L cube. So it will be 3 into 22361 into 0.01042 upon 12.5 cube. So it will come out to be 0.358 Newton per mm. So this is the stiffness coefficient for the cantilever beam. Now we know what is the formula of natural frequency of the system. Second step is to find the K equivalent. We know the uh, uh, stiffness coefficient of cantilever beam, and we know the stiffness coefficient for the spring. So since these two springs are in series that we can clearly see, therefore the K equivalent will be 1 upon K is equal to 1 upon K1 plus 1 upon K2. This formula we saw just some time back. Okay, so substituting the value of both uh, stiffness coefficient of cantilever beam and the stiffness coefficient of spring, we will get the equivalence coefficient as 0.3517 Newton per mm, or we can say 351.7 Newton per meter. So we know the K equivalent now and we know the mass. So the final step, step 3, is to find the natural frequency. And that can be easily find as omega n is equal to under root of K equivalent upon mass. So K equivalent is 351.7 Newton per meter upon mass is 5 kg. Make sure that the units are proper. When we have a mass in kg, our K equivalent should be in Newton per mm. Okay, so doing the calculation, you will get natural frequency of the system as 8.387 radian per second, and that was what was intended from this question, to find the natural frequency of the system. And this system included two springs in series. So we covered a new type of question where the two springs of different properties were in series and were in undamped free vibration state. I hope you are clear with this question. Any doubts up till now? Okay, so let's proceed ahead. Now we will see the third question. This question says, consider the steel frame having modulus of elasticity 2200 GPa gigapascal, shown in figure, having a rigid horizontal member to which a horizontal dynamic force is applied. You can see PT is the horizontal dynamic force applied at the right end of the frame. As part of the overall structural design, it is required to determine the natural frequency of the structure. So in the figure given in the question, we can see we have been given a steel frame whose modulus of elasticity is given. uh, the weight of it is given as zero point 0.5 kilonewton per meter. So per meter length of the steel frame is weighing zero point 0.5 kilonewton, and the total length is given as 10 meter. And we have two columns of length 2.5 mm. Width of those columns are 8 mm, and the depth of the columns are 24 mm. And we need to determine the natural frequency of the structure. I will take a pause of 1 minute so that you can think of how to do the calculation in this, else I will continue forward. Okay, so let's see how to solve this problem. We need to determine the natural frequency of this structure. So this is the structure. Now this structure can be converted into an equivalent spring block system as shown in the figure below, where K is the spring, M is the mass, and Pt is the external force acting on the system. Every time the step one always remains the same, that is the assumptions that we need to make for converting this steel frame into a spring block systems are as follows. First, the mass of the columns are neglected, and second, the horizontal members are sufficiently rigid to avoid any rotation at the top of the two columns. Whenever these two assumptions hold true, then only you can convert the steel frame into an equivalent spring block system. Else, there will be much more complications and you can't convert the system directly. So, always start with these assumptions. See for these assumptions if they are given in the question, or assume by yourself before proceeding ahead. If they say make necessary assumptions by yourself. Okay. So step two is first we need to estimate the system parameters. Now, what is the weight of the frame? It is given zero point 0.5 kilonewton per meter, but our frame is not of 1 meter, it is of 10 meter. So the total weight of the frame would be weight of the frame per unit length into total length. So it is zero point 0.5 into 10, which is 5 kilonewton. So this is the weight of the frame, not the mass. It is the weight of this frame. Second is the stiffness of the columns. Now we have been given with the dimensions L, length, width, and breadth. So we first needs to estimate the stiffness of the column. So the moment of inertia for stiffness we need moment of inertia and modulus of elasticity. Modulus of elasticity is given in the question. We saw 200 GPa, and stiffness moment of inertia we will estimate now. So moment the formula for moment of inertia is bd cube by 12. So b is width, which is 8 mm, d is depth, which is 24 mm. So moment of inertia becomes 8 into 24 cube by 12, which is 9216 millimeter to the power 4, and e is 200 gigapascals, which is equivalent to 1 gigapascal is equivalent to 10 to the power 3 megapascal. So 200 gigapascal will be equivalent to 2 into 10 to the power 5 megapascal. Okay, and megapascal can be written as Newton per mm square. So our units are matching for both E and I. Thus, stiffness coefficient for one column can be written as 12 EI by L cube. When a unit displacement is given to the column, is provided on the column, the stiffness is written as 12 EI by L cube. So 12 into E, 2 into 10 to the power 5 into I, which is 9216, divided by L cube, which is 2500 millimeter to the power cube. So after doing the calculation, you will obtain the value 1.415 Newton per mm. But this is stiffness coefficient for one column. What will be the equivalent coefficient? It will be the sum of both the columns stiffness coefficient, because these two columns are now in parallel. Before this, we saw a case where the springs were in series. Now this case is when the springs are in parallel. Luckily, in this question, the properties of both the columns were the same, so the stiffness coefficient is just two times the stiffness coefficient of one column. But there can be cases where the properties of the material can be different, so you need to remember that you need to consider this is whether the system is in parallel or in series before proceeding ahead. So the equivalent spring constant will become 2 times k, which is 2.813. So now we have estimated the system parameters. So the natural frequency of the system can be calculated as omega is equal to under root of k by m. K we found as 2.813 Newton per mm, that we need to convert in Newton per meter first. So it will be 2813 Newton per meter. And mass is 5 into 5 kilonewton we need to convert into kg, so it will become 500 kg. So remember that always see the units first before reporting any answer, because unit conversion is a very important step when you are doing the calculations. So it will become under root of 2813 divided by 500, and upon doing the calculation you will get the value 2.38 radian per second. So this is the natural frequency of the system that was given in the question, 2.813 Newton radian, 2.38 radian per second. So this solves our third question. Till now we have seen three questions. Three all three of them had some variation. First was a derivation, second we saw a question where two springs were in series, and third we saw a question in which two springs were in parallel. Now the fourth question. I hope things are clear till now. Okay, so let's proceed ahead. So this now we will see the fourth question, which is a practically linked question, which you can even visualize. Okay, so what question says the elevated water tower tank has with a capacity of 5,000 gallons of water, shown in figure, has a natural period in lateral vibration of 1 second when the tank is empty. When the tank is full of water, its period lengthens to 2.2 second. Sorry. Determine the lateral stiffness K of the tower and the weight W of the tank. Tank means empty tank we are talking about. Neglect the mass of the supporting column. So this was the assumption which we saw earlier also, which helps us to convert it into a spring block system. Assume 1 gallon of water weighs approximately 5 kg. So I will give you 1 minute to reread the question and think what has been given in the question and how we will proceed ahead. So let's proceed ahead with the solution of this question. You can see in the diagram there is a fixed base upon which there is a spring. There is a column of stiffness K, and above it there is a water tank of weight W. W is the empty weight of the water tank, and there is water inside also that tank. And we have given a displacement U in the horizontal direction, which sets this spring into an undamped free vibration state. Since there is no external force, so this is a free vibration, and there is no damping also that has been assumed in this week. So this is an undamped free vibration case. So in its lateral motion, the tower can be modeled into a simple accelerator shown below. Since it fulfills all the assumptions, we can model it into a simple Springbok system for our easiness to solve the question. Now, first step is to determine the natural frequency of tank when it is empty. So we have been given two conditions. When the tank is empty, the lateral vibration period of natural lateral vibration is 1 second, and when the tank is full, the period of vibration is 2.2 second. I think there's some new joinee. So I will repeat this question. What this question is. Right now we are discussing a question in which there is a I kindly request everyone to join the sessions on time so that you can be clear with everything that is going from the start. So, right now we are discussing question number 4 of this week's live session. And this question is about an elevated water tank with a capacity of 5,000 gallons of water, shown in figure, and has a natural period of lateral vibration of 1 second when it is empty, And when the tank is full, the period lengthens to 2.2 second, and we need to determine the lateral stiffness K for the tower and weight W of the tower of the tank. And it is given that we can neglect the weight of the supporting columns, and we need to assume that 1 gallon of water weighs approximately 5 kg. So in its lateral motion, the water tower is modeled by the spring block oscillator shown below. Why we can model this? Because it is given that the weight of supporting column can be neglected, and since it fulfills the assumptions of converting into a spring block system, we can convert it into a spring block system. Now, we have been given two periods of vibration, one when the tank is empty and one when the tank is full. So, we first need to determine the natural frequency of vibration of tank. So, the natural frequency of tank when it is empty can be given as when the tank is empty, the natural period is 1 second. Now, we know omega is equal to 2 pi by t. Omega is equal to 2 pi times frequency, and frequency is inversely frequency is 1 upon period. So omega is 2 pi upon time period. And we also know omega is equal to under root of k by m. So equating both the equation, we can say 2 pi by t is equal to k by m. Now, when the tank is empty, the period of vibration is 1 second, and when the tank is empty, the weight of the tank we can write as mt. So 2 pi by t, 2 pi by 1 is equal to under root of k by mt. This is our first equation, which we got from the data given in the question, the natural period when the tank is empty. Now, second, the natural period of tank when it is full. Full means when it is filled with water. So when the tank is full, that natural period increases to 2.2 seconds. So again, omega is equal to 2 pi by t, and omega is equal to under root of k by m. So equating both the equation, we get 2 pi by t is equal to under root of k by m. T is 2.2 second, and m this time would be mt plus mw. Mw is the weight of water. So 2 pi by 2.2 is equal to under root of k upon mt plus mw. Now mt we don't know, k we don't know, mw we know. What it was given in the question, the water capacity of the tank is 5,000 gallons of water, and we are assuming that the tank is completely filled with water when they are talking about when the tank is full. Okay, so and as you, it has been said to assume that 1 gallon of water weighs 5 kg. So 5,000 gallon of water will weigh 5,000 into 5, that is 25,000 kg. Now we have two equation. One is this 2 pi by 2.2 under root of k by mt plus mw, and one equation we saw in the first step, which was 2 pi by 1 is equal to under root of k by mt. So we will square both the equation and divide the LHS and the RHS respectively for both the equation. We'll get 2 pi by 1 ka square upon 2 pi by 2.2 ka square. So it will be 2.2 square upon 1 square. That will appear on the LHS side. And on the RHS side, it will be k by under root of k by mt square will be k by mt, and under root of k by mt plus mw square will be k upon mt plus mw. So k and k will cancel out, and we will get mt plus mw upon mt, and mw we know it is 25,000. So the final equation will come like 2.2 square upon 1 square is equal to mt plus 25,000 upon mt. Now solving this equation, it will be 2.2 square minus 1 square, mt is equal to 25,000, and thus the mass of the tank will come out to be 6510.4 kg. The calculations you can also do side by side. I have solved this question initially, so the values I know directly. So the mass of the tank is 6510.4 kg. This was the first thing that we need to estimate, but in the question we were asked weight of the tank. Mass of the tank is different, weight of the tank is different. So you just need to read the question very carefully before reporting the final answer. So the weight of the tank would be, weight is mass into acceleration due to gravity. So mt times g. G is 9.8 meter per second square. So the weight of the tank will come out to be 6510.4 into 9.8, and when we convert it into kilonewton, it will become 63.8 kilonewton. So kg meter per second square was the unit of Newton, and we converted into kilonewton. So it is 63.8 kilonewton. This is the weight of the tank. And now we need to estimate the also calculate the lateral stiffness K of tower. So we know the mass of the tank, we know the weight, we know the mass of the tank, we know the mass of water. So we can use either of the equation, whether of the natural frequency of tank when it is empty or when it is full. And using suppose we are using the first equation when the tank is empty, so we have 2 pi by 1 is equal to K by empty. We know the value of empty, so just substitute the value of empty and do the calculation. Squaring both the side, we will get K is equal to 257.3 Newton per mm. So this way we estimated both weight of the tank and lateral stiffness K of the tower. I hope this question is clear with to everyone. Any doubts in this question? Arshad, do you have any doubts? Okay, so let's proceed ahead to the fifth question. What this question says: the steel frame shown in figure is fixed at the base and has a rigid top W of weight 100 kilonewton. Experimentally, has been found that its natural period in lateral vibration is equal to 1/10 of a second. It is required to shorten or lengthen its period by 20%, either by adding weight or strengthening the column. We need to determine the needed additional weight or additional stiffness for each case, for shortening or for lengthening. Neglect the weight of the column. So I will. You can see the diagram. There is a simple steel frame structure, two columns supporting a steel frame. The weight of the steel frame is given, and the natural period of vibration of the steel frame is also given. And we need to shorten or lengthen the period by 20%. And for this, we need to determine whether we need additional weight or we need additional stiffness for both the cases. So just read the question and think about it for 1 minute. Else, we will start with the solution. So let's see the solution now. I hope you are clear with the question. So this is our frame column system. First, we need to determine the stiffness of the column. In the question, it has been given weight of the steel frame. The initially the natural period of vibration is also given, but before proceeding ahead with the whether how we can shorten or lengthen the period, we need to first determine the stiffness of the column. So we know the period of vibration and weight of the steel frame. So omega is equal to 2 pi by t, and omega is also equal to under root of k by m. So 2 pi by t is equal to under root of k by m. T is 1/10 of a second. So 1/10 of a second means 0.1 second. So t is zero point 0.1 and m is given 100 kilonewton. but m is mass. And the weight is given 100 kilonewton, we need mass. So mg is equal to w, so m is equal to w by g. So 100 kilonewton, 100 divided by 9.8, so that will be our mass. So 2 pi by zero point 0.1 is equal to under root of k into 9.8 upon 100. So solving this equation, we will get k is equal to 40.243 Newton per mm. So this is the stiffness of the columns, both the columns combined. Okay. Now, second, which is the first part of what we need to solve, we need to shorten the period of vibration by 20%. Now, since we can't reduce the weight of the frame, there are two options for us. Either we can focus on frame or we can focus on the columns. Now, we can't, for shortening the period, either we can reduce the weight of the frame or we can strengthen the column, but we can't reduce the weight of the frame. So, the only possible option we have is to strengthen the column. Okay, so for shortening the period of vibration by 20%, we need to strengthen the column. By strengthening of column, we need to increase the stiffness of the column. So the new period will become 20% decrease means zero point 0.8 times the original period. So zero point 0.8 times zero point 0.1, which is 0.08 second. So therefore, again, omega is equal to 2 pi by t, and omega is equal to under root of k by m. So suppose we need to increase the stiffness of the column by delta k. So 2 pi upon 0.08 is equal to k plus delta k times 9.8 divided by 100. 9.8 divided by 100, why we did? To convert weight into mass. And 42.243 Newton per mm was our actual stiffness of the column. So we converted into Newton per meter, and delta K is the additional stiffness that we need to provide to strengthen the column, which will help us to shorten the period by 20%. So solving this equation, we will get delta K is equal to 22.673 Newton per mm. So by this amount, we need to strengthen the column so that the period of vibration is shortened by 20%. So this is the first part of our solution. Second is lengthening the period of vibration. Now, lengthening can be done either by increasing the weight of frame or by reducing the strength of column. Now, it is not possible for us to reduce the strength of the column. So, one thing that we can do is to increase the weight of the frame. And how we can increase the weight of the frame? By adding additional weight on the frame. So, since we can't reduce the strength of the columns, the only possible option we have is to add additional weight to the frame. So suppose delta W is the additional weight that we are adding. Now in this case, we are increasing the period of vibration by 20%. So our period will become 1.2 times zero point 0.1. Zero point 0.1 is the original natural period of vibration. So it will be 0.12 seconds. So again, 2 pi by t is equal to under root of k by m. Now t is 0.12 second. K will be the original K that we calculated. It was 40.243 Newton per mm. We converted into Newton per meter. And we are adding delta W is the additional weight that we need to add. So it will become 2 pi by 0.12 is equal to under root of 40243 into 9.8 upon 100 plus delta W. So solving this equation, we will get delta W is equal to 44 kilonewton. So this must be the additional weight that we need to put on the frame so that the period of vibration increases by 20%. So we have solved the question problem for both the cases, for shortening also and for lengthening also. And we saw for shortening what we can do and for lengthening what we can do. For shortening, we are strengthening the column, and for lengthening the period, we are adding additional weight to the frame. So this was the solution for question number 5. So in this way, we have covered different kinds of practically related question or additional question that will help you to solve both the assignment of NPTEL and will provide you some much more better insight to the what was the content that was covered in week 1 of this course. Now I will teach you one additional thing, that is how to code everything that you saw, how to see everything visually through a MATLAB code. Now, so as a part of additional learning in every live session of mine, that is every Monday from 6 to 8, I will cover a tutorial of MATLAB wherein I will describe a single degree of freedom system covered in the. I will describe a system that was covered in the week content. So for week one, we will see displacement and velocity response of a undamped free vibration single degree of freedom system. With time, we will see other systems also. So you will get much more clarity of how these displacement and velocity responses change it with change in vibrating system, and it will provide you much more clarity and a new way to learn the same thing. So let's see now. Our objective is to visualize the motion in terms of displacement and velocity of a simple undamped oscillatory modeling structures with a single degree of freedom. And it has been given the initial conditions as u naught is 1 mm and u dot naught is the velocity is zero point 0.2 mm per second, and the natural period of vibration of the frame is zero point 0.5 second. So these are the initial conditions. Since we are talking about undamped free vibration, so in free vibration we need some initial displacement that has been given, and there is no damping, and initial period of vibration also we know. So given the initial boundary conditions, u naught and u dot naught are the boundary conditions. And knowing the dynamic equilibrium equation for a single degree of freedom system, we saw in the sixth module of week one, the solution of an undamped freely vibrating single degree of freedom system is given as displacement at any time t is equal to displacement at time zero times cosine of omega n t plus u dot naught velocity at time zero upon omega n times sine of omega n t. So this is the solution of freely vibrating undamped single degree of freedom system. I guess someone raised doubt. Okay, so there was nothing. Now, so we have seen what are the initial conditions given, and now I will be opening the MATLAB software in my laptop. You can see how to code as of now. If you have MATLAB installed in your laptop, I am giving you 2 minutes to open the MATLAB file and see, you can try to code with me, or you can write the code on a pen or a paper and implement the same later on. And if you have any doubt, you can ask me in the next live session, or you can ask drop your doubts in the nptl forum also. So we will go step by step. We will define every property properly and clearly. Okay, and all the syntax that I will be using are very simple and basic today. So you don't need to worry about anything if you don't have any prior experience to coding in MATLAB. But during this live session tutorials, you will learn a lot about MATLAB and how it can be used for coding a structural dynamics problem. So I'm giving you 2 minutes if you want to open your MATLAB, else I will start. So just open a blank command window. We'll wait for 2 minutes and then we will start. Anyone has any doubt till now? Okay, so let's start with the MATLAB. So our first step is to define what is given in the question, the given values. Okay. You just see the syntax along with me so you can know what is happening. So with the percent sign, everything, anything that we will write will be just comments. It won't be a part of the code. So these are just needed to make the code visually appealing. So what are the initial conditions? First is u at 0, which is equal to 1, and second is v0 equal to zero point 0.2. Okay. On the right side in the workspace, you can see any parameter that you will define will appear in the workspace. So you can cross value verify the parameter value. Now we will define the natural period and the frequency of vibration. Define the natural period and frequency of vibration of single degree of freedom system. Okay. So T is given as zero point 0.5. I will just cross check. T is given as zero point 0.5 second. So if t is equal to zero point 0.5, omega will be 2 pi by t. So omega is equal to 2 times pi. Pi is a pi is equal to 22 by 7. MATLAB knows it takes this directly as in terms of pi, and it will give us the value of it. So omega is equal to 2 pi by t, and you can see on the workspace our omega value is also defined. You can also check it through calculator and you will obtain the same value. Okay, so now we have defined all the given initial values. So the next step is estimation, or we can say problem solving. Okay, so in this, step one is, now we have been given that we need to generate okay, so we need to obtain the displacement versus time and velocity versus time. So how much time? Suppose we take time period of 5 seconds. Okay, you can take 10 also, 15 also, anything. I'm assuming a time period of 5 seconds. So we need to generate a time span between 0 to 5 seconds so that we can have different values between this time, and we can see a plot of displacement versus velocity. So suppose I am generating a time span timestamp of 500 data points. So timestamp is how much data points we want between 0 to 5 second. 5 second is a time of observation. So I want 500 data points between 0 and 5. 5 should have been defined in the question, but I mistakenly forgot about defining the time in which I want to see the displacement versus time and velocity. So I am defining right now the time is 5 seconds. So how to generate this data point timestamp? It is generated like this. T is equal to linspace. 0 is the initial value, 5 is the final value, and how many points we need between 0 to 5? 500 points. So what linspace does, it will divide 0 to 5 in 500 equal intervals. So if you want to divide 0 to 5 in 5 equal interval, it will be 0, 1, 2, 3, 4, 5. Now we are dividing in 500 equal intervals, so it will be 0, 0.01, 0.02, like this. It will define, it will generate a matrix of 500 data points. So this is how we define the timestamp. So you can see here it is a matrix of 1 into 500 points. Now step 2 is to calculate the displacement response. So we have seen the solution of undamped free vibrating single degree of freedom system, which is a cos omega nt plus b sin omega nt. A and b are constant whose value we derived as a is equal to displacement at time t is equal to 0 and b is velocity at time t is equal to 0 upon omega n. So first we'll define these both constant. A is u naught and b is v naught upon omega. NRE. Okay, I mistakenly wrote VO. It is V naught upon omega. So both A and B are defined, and we know the solution of U is equal to A cos of omega t plus B sin omega t. So we know the value of A, B, we know omega, natural period of frequency, and we know the time. So U will be become A times cos of omega times t plus b times sine of omega times t. So this is the equation of displacement versus time for a undamped freely vibrating single degree of freedom system. Now, what is the equation of velocity versus time? It is just a differential form of displacement versus time. So it is, if we differentiate a cos omega t plus b sin omega t, it will become minus a omega sin omega t plus b omega cos omega t. So v is minus a times omega times cos omega t plus b times omega, sorry, a times omega sin omega t. Differentiation of cos is sin omega t plus b times omega. Differentiation of sine is cos omega t. So this will be our velocity response. So you can see on the right side in the workspace, both displacement and velocity response has been defined as a matrix because our time period is of 500 points. So displacement and velocity will be also of 500 points. Now the final step, step 3, is to plot the response. That is to visually see the response. So how it is done? First we will plot displacement versus time. So there is a command known as plot. So plot x comma y. So x is the x-axis, which is the time, and y is the vertical axis, which is our displacement. So we will write plot t comma u, and we will give the title using title command as response. We will label the x-axis as x label, which is time in second, and y label as displacement in mm, the values that were initially given in the question. So you can see, as soon as you will write plot t comma u, the MATLAB will generate a figure. So this is a displacement versus time for a freely vibrating undamped single degree of freedom system having initial boundary conditions as well. So you can see at time t is equal to 0, there is an initial displacement of 1 mm. That was our initial condition. Okay, so this is the response of displacement versus time. You can also save this figure for later on in any format that you want if you want to visually visualize this later on. Like I have saved these figures initially also. So this is the response of displacement versus time. Similarly, we can see how the velocity versus time is varying. So again, plot t comma v. So it will plot. Okay. First, we will apply the labels also. Title is response. X label will be again time, time in seconds. And Y label will be, Y label this time will be velocity. Velocity in millimeter per second. Okay. So I have defined the plot, title, X label and Y label. So let's see the plot. So you can see the velocity versus time response for the initial condition and the period of vibration that we had. And you can see this is not zero. This is starting somewhere close to zero, which is zero point 0.2. Initial velocity was zero point 0.2. So it is starting from zero point 0.2 and it is vibrating. The velocity is changing, velocity of the frame is changing like this for a time scale of 5 second. If you want to increase the time scale, you can increase also. You can see for 10 seconds also, for 1 second, for 2 second, anything. So this is how we visually see a vibration in single degree of freedom system for an undamped free vibration. A system in single degree of vibration, single degree of freedom system in undamped freely vibrating motion. The same thing has been shown in the slide here. The command, everything that we wrote, and the response. So this was everything for the first live session. Now, if you have any doubts, I will be available for till 8 p.m. in the same link. You can ask any doubts if you want, or you can leave if you don't have any doubts. I hope the session was clear to everyone. Mayur and Arshad. Why did we make time period into 500 data points? So Mayur, like we need to see, we know the time period of vibration, it was zero point 0.5 second. Now we need to visually see how the vibration is happening over time, because right now we are talking about undamped free vibration. So we know there, since there is no damping, so vibration, the amplitude of vibration won't change with time. But when we later on we will see about damped free vibration or forced vibration, we'll see that with time the vibration can change. Right now it was not changing, but we took 500 data points so that we can have different points. Now there are different points on these plot which are connected. These all points are connected to make a line. So with 500 data points we are getting these lines, these curves. So all the 500 data points are distributed over these line. So you can see when I'm moving my cursor, there is a black dot appearing. So this is subsequent point. So there are total 500 points on these curves, which is making this wave like picture. I, instead of 500 points, you can also give it 50 points, 10 points. it is just to see the things clearly. The more will be the data points, the more clarity you will get in the obtained results. I hope this was able to address your doubt. The time period was fixed zero point 0.5. It is the time range till which we are observing the motion of the wave, the motion of the frame. You just try with instead of 500 data points, you try yourself with 50 data points, and then you try yourself with 5 data points, and you try with 5,000 data points. When you will try, you will see what variation is occurring, and you will get to know that with more data points there is more clear wave formation. Theoretically, seeing all these things are difficult. That's why I'm covering a MATLAB module also every week. So you can, whenever you have something new in your mind, what if this, what if that, so you can see very quickly and very effectively. Now, theoretically, if you see, you can't make a data set of 500 points and plot on a paper or something. Through MATLAB, all these things will be very clear and will be very easy. So try to follow this MATLAB tutorial regularly, so you till the end you can be very clear with, like, you will learn structural dynamics through MATLAB also as an additional of what you are learning theoretically. Welcome, Arshad. If you have any doubts, you can ask. Uh, Search for MATLAB, simple MATLAB student version. Google MATLAB student version. You may find like online software portal that is available for students for free, or you can ask like if you belong to university or a college. Sometimes colleges also provide free access to students for MATLAB software for like 1 year, 2 years, or something. So you can look into both the things. First, search for MathWorks. The mathworks.com, it is the website where you can see for MATLABs for student. Generally, they provide a free online version for students. Yeah, Mayur. Okay. So there was 0 to 5 second and you are taking 5000 and vectors must be of same length. Okay. So let's let me try in front of you. We'll see. So first are the given values, initial conditions. So u naught is zero point 0.1, in naught is zero point 0.2. That error should not come, but still we will see. And we'll define natural period and frequency. T is zero point 0.5, omega is 2 pi by t. I hope I am sorry I was on mute. So I am writing the code again. So let's see what the result will be. And let's see where we are catching the error. So I'm defining every step of the code one by one. I hope I am audible now. So I've defined till omega. Now estimation. So first is time period. So here we need 5000 data points you are defining. No? Let's see. So here it will come 5000. Now t is 5000. Maybe the error is coming because you again need to calculate u and v. When you are changing uh, the t value, the range of t values, you need to again calculate omega and u and v. Let's see whether that was the error. I guess that was the error. So see, this is a quick way in which you can change some parameter and again define all the values. So just click on the new line and click on the up arrow. So this dialog box opens up where you can easily go and see the old commands and you can define everything again. So we have defined a and b constant. Now we will define u as a function, displacement and velocity vector. Okay, and now we'll see the plot. So you are checking which plot you were checking? Plot of velocity versus time, no? So let me see directly that. So plot t versus v. See, it is coming out properly. When you are changing the timestamp na, to 5000 data points, you need to again calculate u and v because u and v were for initial time span, which was with 500 points. Now your x-axis is having 5000 points, your y-axis is having 500 points if you are not defining them again. So that's why vector must be of same length is the error that is coming. Because at x-axis the vector is of length 5000 points, and if you are not again defining u and v, the y-axis vector is of only 500 points. So that's why this error was coming.